So, right, I'm going to tell you about an ongoing project with David Reuter, and we've spoken about it on and off for a few years because it's been ongoing for a few years. And I thought I might sort of tell you about some part of it that I think I haven't talked much about. But if like, I spoke about this project last week and also a month ago, so if you happen to be in one of those audiences, you didn't see this part. But the title was the same, so I thought I'd mention it. So let me start with something very easy and old-fashioned. So I find that fairly old-fashioned, which is some version of Tanakian reconstruction. And there's sort of an easiest version of Tanakian reconstruction that goes as follows. If you have it's sort of a warm-up. So if you have some category, it's like category, some nice category, maybe linear, whatever. It's yeah, some perhaps linear category. And maybe you give yourself some functor to vector spaces. And you give that functor a name, you call it the fiber functor. And then and maybe perhaps that functor might have an adjoint. Maybe let's assume F has an adjoint. I'm not very good at left and right. Then a thing you could try to do is you could look at, you don't even really have to assume it has an adjoint, but a nice thing to do is that then you can look at some algebra I'm going to mix two things. I can tell that already. So what you can do is you can look at the composition F with its adjoint. And if I get left to right correct, then this will be an algebra monad. This should be the adjoint of F, and maybe I'll just put a check because I can't tell if it's the left or the right adjoint. If anyone can do it in real time, that would be great, and I will correct this. This would be a monad on Vec. Monads on Vec are just the same thing as algebras, yes?
I think it should be a right adjoint.
Perfect, okay. So F has a right adjoint.
Wait, no, sorry. I wrote down left and then I said right. So this why.
Oh.
Really depends what you're going to do with it.
Oh, let's be a monad and not a coma. So then it'll be a monad on Vec. And this is just the same thing. Monads on Vec are the same thing as associative algebras in Vec, just because of some magic property of Vec, because the endomorphisms of the category of vector spaces is the category of vector spaces, if I say the word linear enough times. And this algebra is very nice. It tries to approximate C. So C tries to be, is approximated by the representations, the modules for this algebra. Some piece of whatever you want to call it. Maybe you call it Tanakian reconstruction. Maybe you call it monadicity theorem or something. And this gets more exciting if you assume more properties. For instance, sort of probably the version of Tanakian reconstruction you might read in. Yeah, and as I said, like maybe this should have been right, and I really wanted comonads, and we'll see. There's lots of variations. But another thing you might do is you might take, okay, so let's add some fancy version of it.
Are you saying that the assumptions you put on the board imply the last statement?
This is an approximation sign. This is not an equality. They're just approximately the same. I mean, the statement of monadicity is that this is the algebra whose modules best approximate this category among all algebras. And then you can go sort of add more hypotheses to say that this approximation is very good. Maybe it's a perfect approximation. A priori, it's just an approximation. But in any case, if I have this much data, I can certainly extract an algebra, which is morally just the endomorphisms of this object. You can add some more adjectives. For instance, you could say maybe this is a monoidal category, and that's actually the version I want to talk about. And you might ask that F be a monoidal functor. And if you add this condition, then this monad ends up being not just a monad, but something that might be called a Hopf monad and might not, because it doesn't necessarily have something like, sometimes it's called a Hopf monad. So anyway, this algebra A ends up being a bialgebra. And maybe Hopf. It's not hard to get it to be a Hopf algebra if you put enough adjunctive. So I'd like to redo this same story in slightly better, because I don't really like monoidal structures. I like higher categories slightly better. So
Is there any difference between saying natural transformations between F and itself and assuming there's a left adjoint and defining that monad?
Well, he's doing what you're talking about, Tudor, is more closely related to comonad.
I mean, I was really, as I said, I don't know left and right at all. So maybe I was supposed to put a co here and an R here and a right adjoint there. But no, this algebra just ends up being the same as endomorphisms of F. I'm using the fact that I'm going to VEC in general, it would be something slightly better. And the details are just whether I mean it like it's just the endomorphisms or a more enriched version of it. So if I put an underline here, it's exactly correct, because that's the definition of endomorphisms. Because underline is the sort of thing people do to mean that it's not quite the thing that you wrote. So I'd like to tell this story exactly exactly probably 3 or 4 more times. So
I'm worried.
I'm not a huge fan of monoidal categories. They confuse me. So instead, I prefer to talk about 2 categories. So let me replace C by the category of module categories of C. And I'll think of this in some sort of world of, I don't know, some sort of so this is some 2 category. It's in some 3 category of 2 categories. Let me just write something like 3 vec, but be very indifferent about what that is. Some 3 category. And now I actually have a little bit more than, so now I have 2 data. So this is now it's a 3 category. And my fiber functor still gives me an adjunction between, this is, I don't know, some version of 2 vec. Again, doesn't really matter who that is. So my fiber functor still gives me a map between these two categories. Nice adjunctible map. And I have another functor between these. I mean, there's an adjunction here. It doesn't. Which did we decide? Did we like left or right? So I have some adjunction comes from the fiber functor, but you get another adjunction from the fact that you wrote this as modules for a category. And probably the way I'd like to set it up is that the other one has the other adjunction. So there's sort of a home from C and these functors are basically like C as a C module. So if either, so it's sort of these ones know who C and the modules of C is. So this is the background that I want you to think about. And then the fact that this was a nice fiber functor here actually tells you something. So maybe this will be, maybe my upward arrow is sort of going to be the inclusion, sort of the object C itself, sort of the including object. And well, statement then that you can have, sort of what's magic about this that tells you that it came sort of corresponding to coming from a monoidal functor is that if you have about two different functors, both of which have a left right, and if you go up and back down, there's a nice isomorphism to the antenna. That's the context I want. So the theorem I want to tell you, the first theorem, which will probably take up a lot more than I mean it to take up in my time, is that at this level of generality, when I have a retract in a 3 category, I can get a Hopf-Algebra.
So you're using all 4 of your functors here? Or
So let me state the theorem that I have in mind, and then I'll sort of start to explain it. So the theorem that we proved is that give this some name. Let's so if I wish I hadn't used the letter C already. So given a retract in a 3 category with all adjoints, we get a Hopf-Algebra. I really mean a Hopf-Algebra. So that's the first thing I want to tell you today. I'm going to tell you a little bit about how this works in case you ever want a Hopf-Algebra. I don't know. I know some people in this room like Hopf-Algebras and like building. So this is a way to build some Hopf-Algebras.
And you mean Hopf-Algebra as over a field, or?
Where do I mean it? So let me say this a little bit more precisely. So if I have a retract, maybe what do I have? I have a retract. I have some upstairs object and some downstairs object and some upward arrow and some downward arrow, so that this composition is isomorphic to the identity. Then this is a Hopf-Algebra in, well, I want to say in the endomorphisms of Y. I'm in a 3 category, so the endomorphisms of Y is a 2 category. And so the twice endomorphisms of Y is a graded 1 category. This is a Hopf-Algebra object in the graded monoidal 1 category of kind of twice endomorphisms. Natural transformations of the identity functor. And actually, our theorem is completely coherent but at the level of infinity categories. That's the theorem I'd like to tell you sort of how some of the machinery.
I think this is related to Chris's question. Can you spell out who is X, Y, and which are the 2 maps in the retract? Because you have F, F, L, C, and its adjoint, which are the ones that you claim compose the identity. I'm not seeing.
Okay, so I was imagining that the downstairs person was this one, and the upstairs person is this one.
Yeah.
And if the composition of right adjoints is the identity, then the composition of left adjoints is also the identity.
So for both pairs of functors, you're
Yeah, because if I'm claiming that if you go up and then down, that's the identity, but now take left adjoints to that equation. Let's find it that if you go up this side and down that side, you also get the identity. So those 2 statements are equivalent.
down meaning C and then the F.
Yeah, I go up by like including the rank 1 free module, and then I apply the fiber functor to it. I didn't really tell you who these fiber functors should be. Maybe I got them backwards.
So it's C and F that are the pair, and FL and CO.
That's right.
Yeah, could you give some context of or physical system where this might be relevant? Or
Yes. So typically the case I'm going to care about is when my downstairs, I'll imagine as some sort of background or vacuum object. Where is this an example? So here's a very common situation that you might care about. You might have some nice topological theory. I should really have used more colors than this. So yeah, background could be in white, and upstairs could be in green, and For those of you who have sort of a very common color blindness, this is not helpful colors. But these are the only colors that are in hexagonal order. Right, so what you might have the following situation. You might have some topological theory that you like. And you might know some boundary conditions for it. So a typical situation is maybe, for instance, this might be a sigma model. So this might be some. The typical situation is that X might be some topological field theory, and it might have, for instance, a sigma model, and it might have some, and maybe the downstairs white person will be sort of the vacuum theory. Or some fake vacuum that you're actually embedded in. And a typical situation is that, so then what are homomorphism between the vacuum and your theory? Those are boundary conditions. And a typical situation is that you might have, for instance, a boundary condition, and also sort of be at this level. I mean, I will in a moment put arrows back on these, but everything has adjoints. So I'm not going to really worry too much about that. So you might have something that you might, for instance, think maybe as a Dirichlet. And a typical thing is you might also have, for instance, a Neumann boundary. And a property that Dirichlet and Neumann boundaries have is that they intersect transversely. And the transverse intersection of Dirichlet and Neumann, the fact that Dirichlet intersects Neumann transversely, is that sort of corresponds categorically to the fact that if you go around this circle, that's just the identity on. That's sort of a way of encoding the transverse intersection. And more generally, it's a common situation that you have two boundary conditions with this sort of transversality condition. This sandwich that you form just disappears. And I'm telling you that anytime you have two boundary conditions with enough adjunctability, then you can get a Hopf algebra. And you can do it completely coherent. There's one example. It's not the example I care about, but I think it's the example that people in this room care very much. So I want to tell you a bit about how.
And the Hopf algebra is supposed to be related to the thing that condenses on these boundaries, or is that what's the Hopf algebra in this
I mean, you could ask
this
Twitter
picture?
for some beautiful pictures and I'll draw them for you. And I'm going to give you some beautiful math formulas, some like pure abstract nonsense formulas instead. That sort of handle all the coherence.
So David drew these.
That's right.
So it's like in 3D, the Hopf algebra is the space of states on a rectangle.
Yes, of course, this is the correct answer. So, so the Hopf algebra you get.
Bounded by those two.
As Tudor says, this goes back to about 7 years ago. You can find David's talk at Perimeter Institute, which is the first place that I know of for these pictures. And so in some sense, what we've now done from that perspective is to do it coherently and then use it for some things. Condition here, this condition tells you that if you just take the sort of only two boundary conditions. It's just the vacuum.
Yeah, can you maybe use the blue chalk for arrows and stuff, but not for words? And the glare is too hard to read.
Okay. Yeah, so
sorry, one more question. For the state sum models like Turaya Fira, so I can only find such defects which sort of retract to each other if my theory is based on a Hopf algebra.
that's exactly right. So what I'm telling you, and this is in the trivial, something you already knew. I'm telling you that a Triavero theory always comes with its Triavero boundary, and it comes with another one, which is sort of a transverse condition that choosing a transversality, a sort of a boundary condition transverse to the trivial boundary is choosing a fiber functor on your fusion category, is choosing a description of your fusion category as representations of a Hopf-Algebra. I'll tell you the example in a little bit that we use for this. I think I should tell you the example now. Because I didn't really plan my talk out, so I might as well. But here's another example that we cared about, which was the following. So another example that I care about is in the, this is an example in the category of Bordisms, and Bordisms with boundary. And so in the category of frame Bordisms with boundary, maybe in sort of n+1 dimensions and n-dimensional boundaries. N+1 dimensional, n-dimensional. So in that example, I could consider the following Bordisms. So maybe I should give some names for this. So maybe this is maybe the bulks of my Bordisms. I'm going to draw a typical bulk in white and a boundary condition, so closed boundary in red. By the way, so Bordisms with boundary, Bordisms are sort of bits of material that you can glue together. And Bordisms with boundary, the way you should think about those is that a Bordism with boundary, if you have a Bordism, it has some places that you like to glue along, some sort of surfaces, sort of ends, which are some type of boundary condition of the Bordism. But if you're in the sort of relative Bordism category for manifolds with boundary, there's also some parts of the manifold that you're not supposed to glue. And so the way you really should think about this is that like those are the parts where you've already finished your piece of wood. Those are like coated in lacquer, and glue does not stick very well to lacquer. And the gluing surfaces are places where you still have some raw wood to work with. And of course, this is fine because if you have a full manifold that's kind of, you might have sort of a typical thing you might have, for instance, is you might have some, so here's just a closed manifold in this world. I mean, closed is the wrong word, but so here's a Bordism from vacuum to vacuum because I've put lacquer at the end of the manifold. So this is for instance, this is maybe this is the case I care about. It's maybe n-1 disk. So there's a nice Bordism from the n-2 dimensional empty set to the n-2 dimensional empty set. But because it's a piece of wood, I can chop it down the middle if I want. And now I can write this as a composition of a Bordism. Here's a nice composition from a Bordism. Sorry. Oh, because I'm building up to another formula I'm about to write down, and it will be convenient for me to have this be the dimension that's I need a few more dimensions. I'd really like to, so I decided my bulk manifold should be 3n+1 dimensions. I think the maximum dimension that I can draw reasonably well on the board is 3. So I really better make n+1 be 3 and n+2. And I kind of want to draw a picture in a moment that uses this. So this is the disk with its like n-2 dimensional sphere as its bound. But for instance, you could certainly write this as a composition of here's a Bordism from the empty set to the d-2 disk. In this case, the d-2 disk has, we're sort of looking at an edge on, so you can't see the fact that it has an n-3 dimensional sphere as its boundary, and composed with another Bordism back to. So that's a typical thing you can do in a manifold in a theory with boundary. And here's the actual retract that I want to tell you in our example. Oh. Go forever now. And by the way, sort of, while I'm anticipating it, let me point out that like, here's a bordism composed with its adjoint, which we already said that always sort of gives you a monad or a comonad, depending on whether I'm at the left adjoint or the right adjoint, which is sort of why the disk has an algebra structure. What gives you the pair of pants algebra. Anyway, so the example that we were investigating in this project that led us to wanting this sort of general coherent theorem was the following example. Here's a bordism from correctly. Here's a bordism from this sort of half disk to, I'll draw it sort of in a funny circular way because I'm about, you know, as we said, sort of the Hopf algebra is some sort of square that rotates things around. So here's a bordism from here to here's a handle attachment. I'm drawing it in some specific dimension, but it doesn't matter. So here's some handle attachment, which is in this case I'm adding on. So there's some handle. This is some handle attachment. Doesn't matter which one. Pick any handle attachment. You take some handle attachment on a half disk, and then maybe you do another composition, and because I'm sort of rotating around set as a drawings. But here's another composition. It's the canceling handle. So here's the canceling. Some handle. And all I'm reminding people who know some handle attachment theories that it happens all the time that you do a handle at like the part of sort of one of the pieces of handle attachments that you learn is all about retracts, where you attach a handle and there's always a canceling handle. And so now if you take a picture like this, so here's a retract, and okay, so I decided to draw this sort of in funny ways. This is like, these are mates of the morphisms I want. And if you take these two, this handle attachment and this canceling handle, and ask why do they cancel? Well, the reason they cancel is because, so why is this a retract? The reason these two handles cancel is because you could take, let's see, I need to give you something that cancels the two handles. So really, I should have composed them at some right angle because here I'm going to compose right angles. And so you can take the disk, the fact that this is a disk, and kind of glue it in this sort of into that kind of quarter of the board. And then you can take copies of it 4 ways around to get the other 4 corners of the square. When you start filling in, sort of you fill in that square over there. And what we find out is that the Hopf algebra, or Hopf algebra in this case, ends up being a sphere times a disk. Some sort of disk at the bottom that get out. And so what we find is that bordisms like this, here's a typical bordism with boundary. This is a bordism with boundary from, so sort of this bordism. So this bordism is an element of twice endomorphisms of something. And so this statement is that this corollary of our theorem is that solid torus minus a byte taken out of one side that bordism from empty set to this disk, the Hopf algebra. in from empty set to the disk. Now I guess the n disk. So we produce lots and lots of Hopf algebras. This is the solid n-dimensional torus. Or any, well, okay, there's a bunch of different solid n-dimensional tori, because I could put 6 of the dimensions here and n minus 6 of the dimensions in the other direction. This is sort of what we were doing. So in TFTs, there's sort of a whole zoo of Hopf algebras that a TFT has, all in the same category. Okay, I've used half my time, and now I want to tell you some of the sort of more mathy stuff about how the theorem works, because I kind of enjoyed it. We're writing the paper right now, so it's in my head. So,
I mean, you constructed this Hopf algebra and you didn't remark about this kind of approximation. Is it giving you constructing the projector onto the part of either X or Y given by the retract? Does that make sense?
Yeah, so the idea is that kind of the upstairs object is trying to be representations of this Hopf algebra in some sense, or it's sort of two-dimensional representations.
Right. Yeah, I
But
guess.
I don't have a precise statement like that.
I see. There's not some conditions like in the that would.
I'm sure that there should be, but we don't have them. Like what we have right now is this sort of this direction. Given a retract, I can produce a Hopf algebra. We don't have a kind of general kind of monadicity statement that says that you can reconstruct the upstairs from the Hopf algebra under some condition.
T is a generator.
Yeah, I don't really know what generators are in dimension 2. I mean, I know conditions that are too strong for the reconstruction. I don't have the sharp state. Like I don't have a statement that's not kind of overly strong. So I want to tell you a little bit about how the construction works. And then if I have time, I want to tell you, which I won't, I wanted to tell you a sort of generalization of this, but I won't have time for that, so that's okay. So there's a nice construction that looks a priori completely unrelated. It is a sort of independent thing that I think people should be very excited about right now, that you're seeing lots of papers right now come out, which is called the lax tensor product, or the tensor product. Given various names, maybe you call it a lax tensor product, or the Kranz-Gray tensor product on the category of infinity categories. I want to tell you briefly what this is. So Claudia and I wrote about it a little bit a few years back, and now there's sort of a more thorough treatment. And I think the sort of state of the art is some work by Tim Campion. And I won't give it a precise, I won't tell you precisely what it is. You can read Campion's paper and he gives a completely correct, like absolutely kind of very much sort of in the flavor of kind of abstract higher category theory construction of this tensor product. But the idea of it is the following. So the idea of the tensor product is you think of a category, you think of a higher category, you think of each morphism in a higher category. It's tempting to draw a morphism as a cell. So it's tempting to draw a higher category as having some 0 cells that are maybe the objects, and then some 1 cells, and you know, sort of square of 1 cells, and maybe a 2 cell that fills them in. That would tell you that some sort of commutativity. But in a higher category, everything gets to have a direction. So maybe here's a laxly commuting square. Typical thing that might occur in a higher. And I'll just use the word cell for here. And the idea is that so the first idea, maybe the 0th idea, is that higher categories are like directed cell complexes. This can be made very precise. I'm not going to. And then the second idea is that when you want to take products of cell complexes, the cells in the product should just be the products of cells. And the dimensions should add. The next idea is that you define, if you have a K cell and you multiply it by an L cell, then you make this into some sort of K plus L.
Can you move up the board?
Yes, except then this part gets hidden, so
I can't see.
I guess it's hidden no matter what. Oh, there's a solution. So a K cell and an L cell should be a K plus L cell. And if this K cell, maybe I give them names like A and B. Of course, the cells have boundary, like the boundary of this cell was these two arrows and these two arrows with those directions. And the boundary with total boundary, of course, the boundary of A tensor B, of course, will have to be the boundary of A tensor B, union with the boundary with A tensor boundary of B. And the union is over maybe the boundary tensor the boundary. And then the final thing is to assign directions to this new cell. So by induction, I've already assigned directions to all the boundary cells. And I just have to assign a direction to the new cell. And the rule is that, so what can happen is the following. So here's the type of problem that you run into, and then I'll tell you the solution. I guess my next board's supposed to be over there, so I'm not going to go over there yet. So the type of problem that you might run into is if A is a one morphism, and if B is some other one morphism, the typical situation, then you'd like to define this as a two morphism. Well, okay, the boundary had better be something like a one morphism in these two directions, a two morphism in these two directions. And now you have to decide, there's two directions for the cell to fill in. So the two cell could either go this way, or it could go that way. Those are the only two directions where it's valid to fill a two cell in, because the source and target of a cell have to be parallel. And so the northeast direction, that's the one that the first guy prefers, because it's sort of rough, almost like it's sort of slanted up, but it's sort of roughly going in the same direction as the red cell. And it's going the wrong direction from the perspective of the green cell because it's going up. And conversely, the southwest direction is going is the one that green prefers. And so the two cells might be in conflict. Sometimes they are in conflict, sometimes they're not. But when they are in conflict, the rule is that if there's a conflict, if there's debate, there's never a debate. The first person wins. The first cell. Every debate, the first cell wins, and the second cell just doesn't get a vote. Sometimes the second cell's happy because they agree, but always the first cell gets to be happy. That's the rule. And with Claudio, we confirmed, it was a really fun combinatorial lemma to check that this rule is always valid. That if you just sort of iterate this rule, you never get into problems with pasting diagrams later. It's very fun. So that's the rule. Okay, so now you know the tensor product of cells, and then if you have any big category, you just sort of compile it out of cells, and that defines the tensor product. And the hard work that people like Tim have done is to confirm that compilation step is really valid to do in this kind of infinity categories. So as an aside, this tensor product, because it's defined by by definition, I told you what to do on cells, and then I said, okay, now you extend to categories based on kind of gluing cells together. That definition tells you that actually the tensor product preserves colimits in each variable. And now it's just a pure abstract nonsense fact that if you have a tensor product preserving colimits in each variable, then it has inner homs. What do I mean by that? I mean that the functor tensoring with A as a functor from the infinity categories to itself has a right adjoint. And that right adjoint has a name. That right adjoint is called, well, you can work out what the right adjoint is. With Claudia, we call it the unlax. And I want to flag this does not mean lax functors. This was a sort of something that we couldn't come up with a better term for. So what this means this is functors. So if you take functors from A to C, let me put another C there. So this is functors from A to C, but lax natural transformations. Lax modifications and natural transformations. That's what the lax is. And also tensoring on the other side has an adjoint. Has a right adjoint, which is what the oplax natural transformations. So the same objects, interhalms always have the same objects. It's functors from B to C. Oplax natural transformations.
Sorry, I think you're about to switch the board.
Yes.
I was about to ask you to.
So I'm going to use a slight variant of this.
Yes, how do you see that anything lax comes up from the tensor product of cells?
The laxness is precisely the fact that this is not an invertible morphism. So if you ask, like, what is a one cell, like by definition, like what is a one morphism in this category? So a one morphism in this category would be tested by by mapping from A tensor a one cell into C. And then if you work out what A tensor a one cell is, it looks like it has a bunch of non-invertible cells there.
Am I understanding your notation correctly that this is just some complex inside of the functor category?
So these are infinity categories. Sort of fun lax and fun oplax. There are two different infinity categories that I can assign given categories C and an input A or B. And these infinity categories have as their objects the functors from A to B, from A to C.
Okay, but it's not a subcomplex in this. Never mind. Okay.
Well, so maybe like there's one other thing you might write down, which is that if you take just the Cartesian product, I should have just used the same letter here everywhere. That way I can refer to it 3 times. If you take the Cartesian product, of course, the Cartesian product is symmetric. The Cartesian product on infinity categories also has an adjoint. The right adjoint. Which is what with Claudio, we call the strong functors. But of course, again, these all have the same, it's still functors. It's really functors. A to C, and now strong natural transformations. Natural transformation is called strong if every time you see a commuting square, it actually commutes up to isomorphism.
So the question was, I think you're answering it, which your thing sits inside of the strong one.
My thing sits outside of the strong one.
Strong one sits inside yours.
That's right.
Okay.
So all 3 of these have the same objects. And the strong natural transformations are among the oplax natural transformations, and the strong natural transformations are also among the lax natural transformations.
So you say, so you have the tensor product on this infinity categories.
Yes.
So it makes choices for these filler cells.
The tensor product is the category you get by declaring that a cell in the tensor product is a product of cells in the 2 pieces, and then you assemble a category out of those.
Okay.
In the same way that the tensor product, there was a product on cell complexes, which you just declare a product of 2 cells as another cell, and then you assemble the cell complex out of it. So the definition is that like a 1 cell times a 2 cell is this square, for example. This is the output of that tensor product. So I want a little bit of a variant on this. And then I'll get back to the story I started telling you about. which is that anytime you have a tensor product, you get on some type of spaces, you get a smash product on pointed spaces. So the variant that we needed is you could look at pointed. Pointed infinity categories. These are infinity categories with a distinguished object. And on pointed infinity categories, the natural thing to do is to not look at all functors, but on functors that preserve the base point. And you could define we have like 45 minutes left, right? So you can define a smash product. You have a category with a base point. This sort of smash product. And this is defined as the tensor product. And you smash out the sort of, you force all base points to be the base point. It's a totally natural thing to do if you like pointed, if you prefer pointed spaces. The reason I was telling you all this is for the following example. So this is the inner HOMs for this are like functors, functors and natural transformations, all of which preserve the base point strongly. The reason I was telling you all about this is because now I can tell you almost what a Hopf algebra is. Let me go back to where I started by talking about adjunctions and monads. So there's an interesting pointed category called monad. So monad has a distinguished object, and it has a morphism from it to itself, and some higher and some maybe let's give that a name like A, and there's a two morphism from A composed with A to A. And there's some higher coherence. It's sort of the universal monad, the universal thing. So this is you take the definition of associative algebra, unital associative algebra. Take the definition of unital associative algebra, and you just take the universal thing that defines associative algebra, and you deloop it to a pointed category. This is sort of the delooping of the walking algebra. So maybe it's called the walking monad. The walking associative algebra is the universal monoidal category with an algebra object in it. This is the universal delooping of them. And the example, this is a pointed category because it has, so it by definition has a base point because it came from delooping something. And the fun exercise is to work out what monad smash monad is. This was a very fun exercise because you really have to think through how different cells get turned around as you sort of play with Hom tensor adjunctions. And when you work through how different cells work out, you get the the twice delooping of the walking bi algebra.
Is this something like non-additivity?
Some type
of duality, something like that.
So also what I wrote is slightly false, which I have to fix in a moment. So this is, let me give a sort of, there's a little asterisk right now. I haven't, not quite correct the way I've said it. Yeah, I don't have a good answer to this. You would have expected, some people would have expected maybe the walking E2 algebra. That's like what a non-additive person would immediately guess, but it's not. It's the walking bi algebra. And that has to do with tracking through the fact that half the time my cells get reversed in their direction.
Cool duality type thing.
Not in a way that I see it.
Your walking associative algebra already like de-looped once or something? Like you already
Yeah,
had?
I mean, like my walking associative algebra is sort of an element in a monoidal category, and then I deloop it to an element in a to a two category. I mean, okay, what am I trying to say? To talk about associative algebra, the notion of associative algebra makes sense in any associative category, but the walking associative algebra just isn't a category. It's like a monoidal category.
Let me ask you. Yeah, I guess my question is, why can you de-loop twice on the right? That's the.
Because the walking bialgebra doesn't parse in a monoidal category. To make sense of a bialgebra, you need to have at least a braiding. So this guy, by this I mean the walking bialgebra in a braided category. I will fix that correction. Let me draw some pictures first.
Let's see.
So what is a bialgebra? I think most of you know what a bialgebra is. There's a reason why this can't be correct the way I wrote it. So what is a bialgebra? A bialgebra. Everything I have is unital, but I won't typically draw the units. So what is that? That means I have a multiplication map. And maybe it's unital, and there's some standard associativity laws that you're used to, like some law like that. And all sorts of other axioms like that. And you have a co-multiplication, which is co-unital. And some standard axioms that I don't feel like drawing. And the interesting axiom is that if you multiply and co-multiply, that's the same as co-multiplying and then multiplying. And here is where our discussion with Dave comes in, is that you have to have at least a braiding in your ambient space to draw that picture. Well, this is a bialgebra in a braided two category. This is the interesting feature. And it's Hopf if additionally the map, this sort of shear map, is it's not
Can I ask you a question?
Please.
If you took monad tensor monad rather than smash, would that be like a pair of E1 algebras that weakly associate over one another? Is that...
So it's still, you're going to have some things turning around. So it'll still be sort of have some E1-y stuff and some co-E1-y stuff. But it's more like, it's more, I think you have to put the word weight in a bunch of places. It's more like a bialgebroid. There was a reason I was going to tell you. Oh, right. So I have to correct this thing. There's a reason why this can't be correct, because this is a 2 category. And so if you smash it with itself, you ought to get a 4 category. But this is just a 3 category. So the correct statement is that the 3 localization, this is correct after 3 localization. You're localizing 3. And if you really unpack what monad smash monad is, this bialgebra axiom doesn't hold up to isomorphism, it holds up to like a natural transformation. You on a 4 category, you'd have an error. Oh. I'll totally run myself out of it.
Localizing, so you're inverting higher morphism.
That's right. So I invert this. This is the dimension that I have to 3 localize. So this is a 1 morphism in the 1 category. And so but if I do loop twice, it's a 3 morphism in my 3 category. No, this is I lost track of a number.
Is the motivation for doing that localization just so as to be able to write down this sort of, to be able to say the words walking by algebra, or is
That's
there?
right. So if you, well, the main reason is because I don't know any examples of bialgebras with this, that are like laxly bialgebra. But if you have an example, then yeah, but I don't know any representations of this guy that don't factor through the 3 localization. But that doesn't mean there isn't any. It just, so if you didn't want to localize, then it would be sort of the walking lax bialgebra. And by lax bialgebra, I mean that this axiom holds lax. So the reason I was telling you all this the following. So Here's another pointed category. You can take the walking adjunction. It's just the universal thing that represents adjoint pairs of one morphisms. It has an object. I'll pick one of them to call the marked object. And maybe there's a morphism, some other object, and it's adjoint. So maybe I give these names. Let's give these names. Maybe I have a morphism and it's left adjoint. And the walking monad embeds fully faithfully into the walking adjunction. Well, that's what I told you at the very beginning. I told you that if you have an adjunction, then you can look at some composition and restrict and get a move. And then what we show is that if you take adjunction smash adjunction. So okay, so now here's what we actually did. We computed adjunction smash adjunction. So this has a map to it. Monad slash monad. I told you that this guy is bialgebra. You have to compute what adjunction smash adjunction is. Well, what's adjunction tensor adjunction? So, adjunction tensor adjunction starts to look as follows. It has sort of, if I only knew about the, say, the right adjoint parts, that would look like a commuting square. Look like a commuting square that kind of laxly commutes. But now I want, that's what it'd just be. This is, so here's a picture of like arrow tensor arrow, morphism tensor morphism. And now I need to do two things at the same time. I need to upgrade to being adjunctable. So if I want to upgrade to being adjunctable, then I have to declare that all of these arrows have adjoints. I also have to declare something about this 2 cell, which we worked out with Claudia about what we have to do. And I have to smash out some things. So I have to do two things. So first of all, to get the smash, if I really want the smash product, I have to take all of this part and smash it out to a point. There's the point part I'm smashing out. And to get it to being adjunction, I have to add adjunctability. And so the adjunctability tells you that this ends up being the following. It ends up being, the adjunctability tells you it tells you that F and G have adjoints. And it tells you that some mate of this cell, of this 2 cell, is an adjoint. Not that the 2 cell itself is an adjoint. You have to sort of work out exactly what types of adjunctability you have. And then if you 3 localize, that forces sort of after 3 localizing, and that's all it tells you. That's the full list. And after 3 localizing, it tells you that some mate of this 2 cell is invertible, because you just get to a dimension where there's nothing to be adjunctable other than being invertible. And so what you find out is that adjoint smash adjoint is retract. At least after 3 localizing infinity 3 categories with adjoints.
Relocalizing means inverting 4 morphisms.
Relocalizing means inverting 4 morphisms. And I'm also sort of just forcing everybody to have all adjoints so that I can be a little bit sloppy. And then the content of our theorem, and I think I'll have to stop here. I can't read, said you can't read blue. So maybe I can write in green. So our theorem is that after 3 localizing, and there's a theorem that doesn't require that. Our theorem is that actually this map factors. So this smash product ends up forcing some. So this. The smashing out is very, very aggressive and it actually inverts this shape. That's our theorem. And if I can have so the whole thing's completely natural by construction. And the other thing that we did that I don't have time to tell you about is to develop a theory of sequences, of exact sequences of these things. So we developed a theory of exact sequences of retracts and exact sequences of Hopf algebras. In the second half of my talk, that's what I'll tell you. Maybe you have to next time at the next conference. That'll be the topic. So this, we have a notion of I won't tell you any of this. I'll just announce it. Of retracts. And they give. So I'm told I'm over time.
Have time for -1 question. Maybe let's make that one question, which should be roundly insightful. Clark?
So if you do